All right, here's my video guide for the Chapter 9 closure. I've modified it a little bit, took some problems out, so it just focuses on what we did in Chapter 9. We have 4 problems that I'll do in a video, and then we have 3 homework problems. A little bit longer homework, but they address some of the things I want to see if we know how to do in Chapter 9, and will help us with the review for Thursday. Um, the idea is just to recap the main ideas. I'm going to be flipping back and forth between my slides, a little bit of the ebook, and then the e-tools, like I've been doing for the whole second half of Chapter 9 here. And with that, we'll just get right into it. It says on paper, KA, which I don't know if that's how you say it. I think maybe it's just K, has a line with points A, B on it. Explain how she can use a compass to find point C so that B becomes the midpoint of a new line AC. All right, we don't use compasses because we've been doing it online, and so this is a Desmos e-tool problem. And what I'm going to do is I'm going to create a line AB and then create a line AC so that B becomes the midpoint. All right, so I'm going to open up my e-tool here, and I'm going to create a line AB. Could be any kind of thing. We'll make it like this. We'll make the first point here A, second point here B. All right, and the way I'm going to go about now creating it so that B becomes the midpoint of a bigger line AC is I'm going to take a circle, and I'm going to make B my center of the circle, and I'm going to extend it so that it has radius to A. I'm going to drag that down just a little bit so you can see the whole circle. All right, and the reason I'm doing this now is because I have this distance AB, which is a radius, and I can create another distance BC from the other side of it that is the same length as AB. And it's not going to be perfect because I cannot do it perfect on here, but now I have this point here, if I can make it C here, where I have my line AC, and I know that AC is twice as long as AB because you had one radius and then you added another radius, or now you have a diameter, so it's twice as long, and that must mean that B is the midpoint. Another way to think about it is that B is the center of the circle. You got one radius out to here, another radius out to here. It's twice as long. And B must be the midpoint of that diameter, really. And that's the way I would go about it and explain it. I take a screenshot of it to put in my slides. And I could do a short description, but for time reasons, I'm not going to. I am just going to say that to do this correctly, we want to make point B. We want to make point B the center of a circle, and then extend it so that you have a diameter. And then I know that's really small, but just for purposes of showing, that's what I want us to do is copy and paste that picture. All right. Now let's move on to 911. Sorry, 9-111. Assume that the solid at right has no hidden cubes. On graph paper, draw a front, a right, and a top view of the solid, and that's where we'll start. Problems like this one here, where it wants us to draw the front, the right, and the top views of the solid, what I recommend doing is, on this problem, I'm going to go to the ebook and open up their e-tool for it, right here, the 9-111 student e-tool. And it's going to give me the shape, and that's going to help me do this problem. But maybe we do a problem either on like the review where it's not so accessible. My recommendation is that you still click on this e-tool, or you go back to some of the earlier lessons where they had those e-tools to build them. And I recommend that you do build it, because just having this ability to do the front, the right, and the top view makes our life so much easier. And, you know, maybe we could say like this, you know, we could deconstruct it and construct it again. But for time reasons, I don't want to do that. But just make sure that we do use these e-tools, because I don't think personally these, I could maybe do the front, the right, the top view, but it's much, much easier having this tool in front of us. Just like if we had like blocks in class, it would be much, much easier. But with that, we can start making these. And so the first one we want to do is the front view. And so I have my graph paper down here, and on yours you should have graph paper as well. I want to draw what that front view looks like. So I'm going to flip back and forth here. I'm going to look at the front, and it goes 4, 3, 1, and so that's how I'm going to draw it on mine. I'm going to take mine here and do just, and then mine is just going to be kind of messy here. 4 and then 3 and then 1, and that's my top view. Sorry, that's my front view. My right view here is going to look like 1, 2, 4. So we bring it back up, and the right view looks like 1, 1, 2, 4. And then the top view is 2, 3, 1. And so I'll bring that back up, 2, 3, 1. And go 2, 3, and 1 for the top view. All right, and I should say that this is front, this is right, and this is the top. All right, again, make sure like either it's, you know, going into that one and just deconstructing it and constructing whatever the shape might look like, because on the review, I think you do have to draw this out, and those tools just help us do that. The next one, we're going to find the volume and surface area of this shape here. And volume's not too bad because we can just count the blocks, but surface area gets a little tough. And again, that's why I recommend doing this on the E-tool, because especially for me, it's hard to count that surface area otherwise. But let's start with the volume. Volume is just a matter of counting the cubes. And so if I go on here, I'll take the isometric view. I know I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so I have a volume of 12 because there's 12 cubes. Surface area is a little bit tougher because you got to count all the faces you can see. And so I'm going to bring it back up. And what I like to do is look at the front, and because you can see all the front faces. And we have 1, 2, 3, 4, 5, 6, 7, 8 in the front. 8 in the front. On the right, we have 1, 2, 3, 4, 5, 6, 7. 7 on the right. From behind, we have 1, 2, 3, 4, 5, 6, 7, 8 again. And then on the right side here, or sorry, the left side I should say, 1, 2, 3, 4, 5, 6, 7 again. And you can see I'm just adding up all the faces here. All right, and then the top and the bottom are always the same. Whatever it looks like on top looks like it's on bottom. So 1, 2, 3, 4, 5, 6. But that's really 12 because the bottom's the same. So we add another 12 onto here, and then we can add it up and get our surface area. 8 plus 7 is 15. 15 plus 8 is 23. Plus 7 is 30. Plus 12 is 42. And that's units squared, because it's a surface area, and this is actually units cubed up here because that's a volume. But right there we have our volume and surface area of this shape up here. For part C, it's asking which net, these are nets down here when you can kind of like, I always said, like a cardboard box getting broken down. Which net has the same volume as the solid that we just did? And so it's saying which one of these nets really has a volume of 12. And there could be multiple ones, and so we'll start with number 1 here, or the first one. And we see that this part in the middle here, this 4 in the middle, is kind of like what I see as our base, kind of the thing that we'll fold into. And that means that we have a length here of 2. We have a width here of also 2. And we have a height, say this gets folded up, we have a height of 4. Sorry, no, we have a height of 3, it looks like. I miscounted it. Now, I know if we're talking about a rectangular prism, which this would be if we folded it, the way we can do volume of a rectangular prism is length times width times height. and that's what I have right there. And so I can do the volume is equal to 3 times 2 times 2. Well, 3 times 2 is 6. 6 times 2 is 12. And so I have a volume of 12, which means that this first one does work. Okay. Number 2, I can't even really tell you where the base would be on this one. It looks like we might have a base. I don't know where it would fold up to that this would work. And so I'm certain, like, I can't pick this out. These other ones I can see where it could fold and create. This one I don't see it. This one I don't think it's possible. This one doesn't work. Okay, this right here, now I have my base right here. Again, you can kind of see like this would fold up, this part would fold up, this would fold up, this would fold up here. And so I know my part right here is my base. And that means this is a length of 3 for the base, a width of 2 for the base, and when this folds up, it has a height of 2. Using my length times width times height, I get a volume that could be 3 times 2 times 2, which gives me a volume of 3 times 2 is 6, 6 times 2 is 12, and that looks like number 3 would work for us as well. All right, so in part C, 1 and 3 work for us because they give us the same volume of 12, and 12 was the volume we got for our shape up here. All right, and then that's 9-110 and 111. Let's talk about 9-112. I think I can get part A done before this video ends. And so they took the shape from the last problem from 9-111 and brought it back here. And it says, if this solid were enlarged by a linear scale factor of 4, what would the new volume be? And what would the new surface area be? All right, so the first thing I'm going to do on this problem is talk about all the different scale factors. All right, so in part A here, I'm going to switch back to black actually. In part A here, it says we have a linear scale factor equaling 4. Okay, which means my area scale factor is going to be 4 squared, because area scale factor is always your area scale factor is always your linear scale factor squared, and so that means my area scale factor is 16. And then my volume scale factor is going to be 4 cubed, because it's always my linear scale factor cubed, and 4 cubed gives me 64. All right, and then actually the rest of the problem isn't so bad. What we do is we take we'll start with the volume, because the volume kind of comes first. We start with our original volume, which we said was 12. And then we take our original volume, which is 12, we multiply it by our volume scale factor, which is 64, and that's going to give us our new volume. I need to grab my calculator quick. And we can do 12 times 64, gives me a new volume of 768 units cubed. Okay, and all that is, that's old volume multiplied by volume scale factor to get your new volume. That's all that is right there. All right, similar kind of thing for surface area. You take your original surface area, which we said was 42. But because this is an area, we don't use the volume scale factor. We have to use the area scale factor. So we take our 42, we multiply it by 16, and we'll get our new surface area. So 42 times 16 gives me a new surface area of 672 units cubed. Sorry, units squared, because it's an area. And then the idea behind this is, again, this is the original surface area multiplied by the area scale factor to grow area, and you end up getting your new surface area here. All right, perfect timing here. I'll finish up B and the last problem in the next video.